So in this video, we're going to be proving this theorem. It says, let f and g be differentiable functions and put p equal to their product. So p of x is f of x times g of x for each real x. We want to show that p is differentiable and the derivative of p is equal to the derivative of f times g plus the f times the derivative of g. You may know this as the product rule in differentiation in calculus, and we're going to prove that theorem right now. For this proof, we're going to be using the definition of the derivative. So we say that p prime of x is actually equal to the limit as h tends to 0 of, so p of x plus h minus p of x all divided by h. Great. And now we want to substitute back in, so we know that p is equal to f times g, so I'm just going to bring it all down here. That's going to be equal to the limit as h tends to 0 of f of x plus h times g of x plus h minus f of x times g of x all divided by h. Now here comes the trick. What we're going to do is we're going to introduce a new kind of plus and minus thing, which means we add something to this fraction and then take away the same thing so as to not change the value of the fraction. So what we're going to do, we're going to say that this is equal to the limit as h tends to 0, much to write a bit small here, of f of x plus h times g of x plus h. And what we're going to add and subtract is f of x times g of x plus h. So we need to take that away as well. So we get take away f of x times g of x plus h, and then we've still got the take away f of x times g of x on the end, and that's all divided by h. We can go ahead and bracket some terms. So we're going to say that this is equal to the limit as h tends to 0 of, so we're going to first look at this first term, and we're also going to look at this third term here. So we say that f of x plus h times g of x plus h, that's going to be a plus there, minus f of x times g of x plus h all divided by h, and then that's plus, we're going to limit again because the limit is distributive, of h tends to 0 of. Now we're going to look at the second term and the fourth term, and then we get f of x times g of x plus h, apologies for my crude handwriting, I'm trying to squeeze it all in, minus f of x times g of x, there you go, all divided by h. Great. What can we do now? We can actually go ahead and factor some common terms out, some common factors if you like. So in this first one, we have a common factor of the g of x plus h. We see that in both terms on the top. So we can go ahead and pull that out front. So we get g of x plus h times the limit as h tends to 0 of f of x plus h minus f of x all divided by h. And then that's added to, we're going to take out another factor. We're going to take out this time the f of x, because we see that in both of them, plus f of x times the limit as h tends to 0 of g of x plus h minus g of x all divided by h. My apologies, this, because it contains an h, should actually be in here. So I'm just gonna just put that down here. So I'm gonna say that's limit as h tends to 0 of g of x plus h, and then we'll factor in here. So f of x plus h minus f of x over h, and then that just stays the same there. So yeah, sorry, it's because there's an h in this g, so when you take the limit you have to consider it as part of the limit. Anyway, for the next bit we can actually go ahead and rewrite this as, well, okay, well, as h tends to 0, g of x plus h just simply becomes g of x, because the h goes to 0, and we know that g is differentiable. And then this term in this square bracket I've written here, this is actually just the definition of the derivative of f. So that is f prime of x. And then this other thing up here, this thing, circle that, that is going to be just this f of x we've already got out the front. And then inside the limit we have the definition of the derivative of g. And if we want to rewrite this, we actually get, we actually get f of x times g prime of x plus f prime of x times g of x, which is pretty much what we had up here. So we've actually shown that the derivative of the product is actually given by this product rule, and we have shown it rigorously using the definition of the derivative.